Okay, today we're going to look at the derivation of Kepler's third law. This law deals with an object orbiting this is a circular orbit another. Okay, so by dynamics we have here, I'll just draw some object. Here's another object orbiting that object. As we have discussed, it has a velocity tangential. It has an acceleration toward the center of the circular path that is transversing. And then we consider the forces acting on that object. In this case, that force will just be the force of gravity between the two objects. So now we look to form our equation. Dynamics equation for this is going to be the sum of the forces acting to create that centripetal motion. In this case it is Fg equals MAC. So Fg is not going to be m times g as it is if we have something sitting on the surface of a planet. Instead it's going to be the larger form of that equation, universal constant times the mass of the planet, or object being orbited times the mass of the orbiter over the radius of that orbit, which is a center to center measurement. That equals the mass of the orbiter times, and the substitution we'll be using here is 4 pi squared r over t squared, a derivation that we looked at in the last lesson. You may want to just pause this and make sure you have the definitions of each of those variables so when you're reading problems you are able to recognize what that problem is referring to. From here we just rearrange this. So I'm going to move all the constant values. Universal gravitation constant will remain constant. 4 pi squared is not going to be changing for anything orbiting that object. And the mass of the thing being orbited, if it was to remain constant, which we presume it to be, then we'll have that also on the side of the constants. So rearranging this, we end up getting and so you can see that the masses have canceled. So we divided it through. And we end up seeing that the mass of the orbiter is no longer mentioned. So we have some constant value here. So this constant is called Kepler's constant. And by looking at it, you recognize that this is just constant for the object being orbited. So it will be changing. It'll be different, I should say, for different objects being orbited. So the Kepler's constant for the Sun, we just put a K for this constant, is going to equal the universal gravitation constant times the mass of the Sun divided by 4 pi squared. Kepler's constant for the Earth will be the universal gravitation constant times the mass of the Earth divided by 4 pi squared. So a constant exists for each object. And that constant will be equal to the ratio of r cubed over t squared for any object orbiting. So it doesn't matter if I'm comparing a satellite about the Earth to the Moon, which also orbits the Earth. They both have this same Kepler's constant. And so therefore, if I found the radius of orbit of the Moon cubed divided by the period of orbit of the Moon about the Earth squared, it will equal the radius of orbit of the satellite cubed divided by its period squared. So we have here 4 different variables. If I'm given 2 of them or 3 of them, I should be able to find the third. Doesn't matter which is the unknown. I may also find on my formula sheet these constants are given and these constants are given. So often the problems are going to be around those types of things. An insight that you're going to want to have in mind is that this r that's being mentioned is the radius of orbit. It equals the radius of the orbited body plus the altitude plus the radius of the orbiter. So these are all of the variables that you're going to have to be considering as you're solving any of these problems. Identify yourself with these variables before you start solving, and you can start this problem at a statement of the Kepler's constant or as a circular motion problem. Either way, you should find yourself exposing all the variables you will need to consider.